Okay, welcome to our third part of our video series. And today we're going to talk about basic linear algebra operations and see how they are involved in GWAS and GS. And then finally reveal the good news that some R code will do all these linear algebra operations for us. And then after we go through the slides, I'm going to briefly show how to do basic linear algebra operations in GWAS and GS in real time in the RStudio. Okay, so some basics of linear algebra. Instead of thinking about things in terms of numbers one at a time, we can think about more object-oriented things. So we got a bunch of numbers that we consider at one at a time. So there are two basic configurations used in linear algebra. We have vectors and matrices. A vector will consist of multiple numbers arranged in one column or perhaps in one row, as we'll see in the next slide. So here are two vectors, x and y, that each are column vectors and each have two elements. And if we expand upon vectors, we have matrices, which have multiple rows, multiple columns. So here we have two matrices. Each of them have two rows and two columns and consist of four numbers, of four elements. And we call them 2 by 2 matrices because they have, respectively, two rows and two columns. And here is the R code of how to create these exact same vectors and matrices in R. Next thing we're going to talk about is our first linear algebra operation, and this is transposing. Now the way I always think about transposing is we're going to turn our rows into columns. Okay, so here are two column vectors. We're going to take the transpose, and so we're going to turn the rows into columns, or more appropriately here, turn the columns into rows. And so X transpose turns from a column vector of two elements to a row vector of two elements, and we use the prime sign to denote the corresponding transpose of our original object. In a similar fashion, for matrices A and B, which were introduced in the previous slide, we're just turning the rows into columns. So in A, the first row is 1, negative 1, and then in A prime, the first column is 1, negative 1. And we use the T function to transpose objects in R. And of course, when I say objects, I'm referring to matrices and vectors. Now, the next thing we're going to talk about is addition. And if we have two matrices that have the same numbers of rows and columns, like we do here for A and B, both have two rows, two columns, we just simply add their elements, their numbers together. So for example, if I wanted to take A plus B, I'll go 1 plus 1, which is 2, negative 1 plus 0, which is negative 1, etc., etc. And hence we get our matrix A plus B. And then we use the plus sign in R to do addition in linear algebra. Now, next thing we're going to do is talk about matrix multiplication. So, we have matrix A, we have matrix B. You can do matrix multiplication whenever the number of rows of the matrix on the left is equal to the number of columns in the matrix on the right. Okay, so let's see. Matrix A has two rows, matrix B has two columns. Good, we're all set. We can do matrix multiplication. So it's kind of complicated. I have the formula written out here. I will illustrate this for the first row, and then we'll move on. So basically I'm going to take this times this plus this times this and add them together, and I get 0. So using this operation here, percent asterisk percent, that performs matrix multiplication in R. So now a little more abstract concept in linear algebra that's going to be extremely important is the identity matrix. So identity matrices are always square matrices, okay? So what we mean by square matrices is number of rows is equal to number of columns. So here, this is a square matrix. Number of rows is equal to 2. Number of columns is equal to 2. Incidentally, matrices A and B were also square matrices. So anyway, and what makes an identity matrix an identity matrix is that the diagonal is going to be 1s, and then all of the off-diagonal elements are going to be 0. Now the reason why we care about identity matrices are that they are basically the matrix equivalent of 1, okay? And so if you remember back to non-linear algebra, working with scalars, 1 had some really desirable properties, right? So anyway, so using the diag function will create an identity matrix. So here we have diag 2, so this will create a 2 by 2 identity matrix. So the reason why we care about identity matrices is that we want to talk about inverting a matrix. So basically, as I say down here, an inversion is basically a reciprocal, is like the linear algebra equivalent of reciprocal. So if we have a square matrix A, it is invertible if there exists another square matrix such that if you multiply A by its inverse, you get the identity matrix. So here's A, here's the inverse of A, and we just let our package solve it for us, and we get our identity matrix. So the solve function will calculate the inverse of A, and so to prove that A inverse is the inverse of A, we just multiply A by A inverse, and we get basically the identity matrix. Note that this is an extremely small number, so we're getting the identity matrix. So now we're going to talk about how linear algebra is used behind the scenes in GWAS. So let's consider the unified mixed linear model. Our y variables are phenotype of interest, and then we include our tested SNP as explanatory variables. We have fixed effect covariates to account for population structure, random effects to account for mealy relatedness, and then our grand mean and our random error term. So at each marker, we're going to fit this model, and we're going to obtain estimates of all of these parameters, and linear algebra is used behind the scenes to provide these estimates. Briefly, this is how it's done. So here we're just re-expressing the unified mixed linear model in terms of linear algebra terminology. So we have a vector of phenotypes, our grand mean multiplied by a vector of 1s. We have a vector of fixed effects to account for population structure. Our marker effect is included here. We have our random effects of individuals to account for familial relatedness. We have our random error term. And this MVN just means multivariate normal. So imagine a normal bell-shaped curve density function, and we have it for multiple ones. That's a multivariate normal random variable. So these linear algebra operations are done here to obtain our estimates and predictions of our parameters. And so GAPIT does all these calculations for us behind the scenes, as we'll see momentarily. Now, here's the ridge regression linear best unbiased prediction RR-BLUP model for genomic selection. Let's do a recap from video 1. So our y variables are phenotype of interest. We have our intercept. We are also including all p markers throughout the genome as random effects. And then we have our error term. The predictions, the BLUPs of our marker random effects are subject to the ridge regression penalty. So to make the transition to thinking of the RR-BLUP model in terms of linear algebra, we're going to talk about an equivalent model, which is the GBLUP. And here it is, expressed in linear algebra notation. So our phenotype is our our vector phenotypes is our y variable. We have our grand mean. And instead of having all p of our markers explicitly included as explanatory variables in our model, we instead have our individuals as random effects. And then we have a random error vector. And then all of the marker information is incorporated into the same kind of kinship matrix that we use in the model for GWAS. And then anyway, these linear algebra operations are used to obtain our BLUPs for individuals and our grand mean. So anyway, the RR-BLUP software package will make these calculations for us. So now that this presentation is done, let's go onto our R GUI over here and start from scratch and do all the linear algebra operations and whatnot. So here's how we create our vectors x and y. Here's x and here's y. And then here's how we create our matrices A and B. So we got A and we got B. And then here's how we transpose A and B. So here's A dot prime and here's B dot prime. And then here's us conducting matrix addition. So here's C. Here's us performing matrix multiplication, D, and then here's us creating a diagonal matrix. Here's our identity matrix. Here's how we calculate the inverse of our matrix A that we've talked about in the presentation. And then here's the proof that this is truly inverse. And remember that this is a really small number, arbitrarily close to 0, or really pretty darn close to 0. And then this is just 1 expressed in scientific notation. So now I'm going to type in this command, rm list equals ls. I'm going to clear our workspace. I'm going to run a really simple GWAS. So here's me doing GWAS in R. And you can go get some coffee or something right now because this will take a couple of minutes. Don't worry, I'm still here. See, while we're running all of this, GAPIT is producing all of our GWAS results inside of this folder. See, just created our kinship matrix that I was talking about. And it's done. Okay. So here's our Manhattan plot showing our GWAS results. X-axis is our physical base pair position. Y-axis is our strength of association between our marker and trait. These data are in maze, and we see here's our peak association on 5. Incidentally, this is the same peak that I showed at the beginning of Figure 1 video when I introduced linear algebra, or when I introduced GWAS. So now let's run genomic selection. This is using RR-BLUP. Let's clear our workspace. And press this button, and we let it do its thing. So let's go to our genomic selection example. Okay, it's doing its thing again, and everything is fine. And let's see. What do you know? We have our results. So here's our results from genomic selection. And if you're interested in looking at this a little more, you know how to reach me. I want to give you my email. And I'll do one right now. So it is, let's see if this works. Nope. Okay. It is ALIPKA at illinois.edu. Thank you. Bye-bye.